We want to use a limit comparison test to show that the series converges or diverges. So let's start with the sum from n equals 1 to infinity of n over n squared plus 1. So if I was to approximate this for large n values, this is basically n over n squared, which is 1 over n. So 1 over n will be a very good candidate to compare it to my original series. And so first it's good to go over the conditions for the limit comparison test. We want it to be positive and decreasing. Okay, so obviously here we're working with n equals 1 to infinity, that's positive, and the denominator is bigger, so we would expect this to decrease. Okay, so it doesn't matter how we divide this. Basically, we needed to divide my original series with 1 over n. So again, you could do 1 over n divided by n over n squared plus 1, or 1 over n, or n over n squared plus 1 divided by 1 over n. Doesn't matter the order in which you do it. Okay, so for this one, I'm just going to rewrite it, and dividing by 1 over n is the same thing as multiplying by n over 1. So that would just be n squared over n squared plus 1. And so this limit will just be 1. And because you get a finite answer, either both converge or both diverge. So it's greater than 0, the limit is greater than 0 and finite, so either both converge or diverge. So this one we have to see 1 over n. We know that 1 over n is a harmonic series. We know that's going to diverge, so there's no way that both can converge. So we say that both diverge. So the original series also diverges. Okay, next example. N equals 1 to infinity. 2n squared minus 1 over 3n to the 5th plus 2n plus 1. So I want to use the limit comparison test again. So I'm going to really approximate this. You always look at the highest degrees. So it's 2n squared over 3n to the 5th, which is 2 over 3n cubed. So I want to compare it with 2 over 3n cubed, but because I'm kind of lazy, I could just do 1 over n cubed. It doesn't matter. So why don't we just do 1 over n cubed? We'll take the original divided by 1 over n cubed. So if you want, you can be smart about selecting your coefficients. Like you could pick something else if you want, but the whole point is it doesn't matter. Okay. Yeah, so I'm dividing by 1 over n cubed, which means that I need to multiply by 1 over n cubed. And this should be a limit, not a sum. Okay, so I'm going to multiply the top by n cubed. So I want to distribute it to both the 2n squared and the negative 1. So I have 2n to the 5th minus n cubed over 3n to the 5th plus 2n plus 1. And the limit. So because we're looking at n approaching infinity, we don't really care about these guys. And the n to the 5th will cancel, and you get 2/3. So the limit is positive, finite, and of course we should always test the conditions for the limit comparison test. But for the purpose of this video, all of these will satisfy the limit comparison test. Okay, so that means that either both converge or both diverge. What we decided to compare it with is 1 over n cubed, which we know by the p-test converges. So that means that both series have to converge. All right, next example, we have a sum from n equals 1 to infinity, 1 over n times the square root of n squared plus 1. So, this looks roughly 1 over n times the square root of n squared, which is just 1 over n squared. So that's a good candidate to compare it to. So we're going to take the limit n approaching infinity my original series over 1 over n squared. Dividing by 1 over n squared is the same thing as multiplying by n squared. So that's going to be n squared over n times the square root of n squared plus 1. So here there's multiple ways to do it. Let's see. If you want to be lazy, you can say, well, this is roughly n squared over n squared, so this should go to 1. Another way to do it is to divide everything by n squared. So I'm going to divide the top by n squared. That'll be 1. And then I can divide this n by n. And then the inside by the square root of n squared. Right, because the square root of n squared is n, and then times the n out here will give you n squared. So it looks something like this, which I can simplify as 1 over the square root of 1 plus 1 over n squared. Now we know that 1 over n squared is going to go to 0. So you have 1 over the square root of 1 plus 0, which is 1. And notice that is exactly what we said over here. Okay. So whether you're lazy or not, you still get the same answer. And so we said that the limit is 1, it's finite, it's greater than 0. So then either both converge or both diverge. Because we compared it to 1 over n squared, 1 over n squared converges by the p-test. So we say that both series converge. Okay, last one. We have the sum from n equals 1 to infinity, sine of 1 over n. This one's a bit tricky. Doesn't seem very obvious what you need to compare it to, but this 1 over n should kind of give you a hint, hopefully. So it will be a good candidate to compare it to 1 over n. All right, so we'll just take the limit as n approaches infinity, sine of 1 over n divided by 1 over n. Now this limit looks complicated, and you may be tempted to use L'Hopital's rule, which is completely fine, because you would get sine of 0 over 0. So it would be 0 over 0 basically. If you use L'Hopital's rule, take the derivative. Actually, let me just show you the steps, and I'm going to show you how you could just be a little... you don't have to do all the work, because the derivative sine of 1 over n will just be cosine of 1 over n times the derivative of 1 over n. So I'm just going to write that as 1 over n prime. And then you need to take the derivative of the bottom, which is 1 over n prime. But it's a complete waste of time to do it, because these are just going to cancel. And so you basically have cosine of 0, which is 1. So that's one way to do this. Let's say if you don't feel like doing this, you can also do a substitution. Let me just rewrite the original limit. If we let's say, x equal 1 over n, we know that as n approaches infinity, x will approach 0. Because x is 1 over n approaches infinity. That means 1 over n also approaches 0. So x will have to approach 0. So now you could just rewrite your limit in terms of x. So x will approach 0 of sine x over x. And we know that is 1. So this one is something we memorized back in Calc 1. So regardless, you do get the same answer. So we had 1 here and 1 here. The point is, the limit is 1. It's positive. It's finite. And either both series will converge or both will diverge. The comparison we used was 1 over n. We know that 1 over n diverges, so we would expect sine of 1 over n to also diverge.